So we're going to have our next speaker, Anthony, speaking now. He'll be speaking about brain and computing. Anthony is a director of IgnitePune02. So, Anthony, over to you.
In computing, hello everybody. I may skip a couple of slides because I didn't know it was that strict. Okay?
Here's a way to skip the slide.
Yeah, brilliant. Okay, so today I'm going to talk about brains and computing. Briefly about my background, I'm just going to skip this very briefly. I'm from Europe, as you can probably hear. I did some neuroscience at university, but at the moment the web is my home. So as you mentioned, some of you here may know me as one of the co-founders of IgnitePune02. Currently I'm working with Sapna Solutions, another web development company I just co-founded. I want to start this with a quote. Okay, everybody knows Woody Allen, and everybody likes to do certain things. But one of my favorite quotes is the brain, my second most favorite organ, okay, by Woody Allen. So let's learn a bit more about the brain and about how this may impact us in computing later. Okay, a brief context. Neuroscience, as you can see, is generally the scientific study of the central nervous system. So that's what makes us all tick. Informatics is, well, as you probably all know, it's related to computer science and information processing. What we will be looking into is neuroinformatics and neuromorphic engineering, which is sort of the merger of both. Okay, and that's, for example, what I did at my university. Okay, in a nutshell, what is the brain? The brain, basically, think of it as a sponge-like, if you want, paneer-like sort of sponge that is sitting in a salty soup of ions, and it consists of nerve cells, neurons, and synapses primarily. And actually, the brain is not this little thing that we have in that Homer Simpson has in the middle of his head here, but it actually, if you want, it extends into the sensory bit. So your brain starts inside your eye, it goes down to your central nervous system. Not to the surprise of most of you, you'll probably learn that the stomach is actually, I wouldn't say it's part of the brain, but it's very, very closely linked to the brain. And as you all know, when you're nervous, when you have to make a decision, gut feeling, all of these things, it's not a coincidence. Like when an embryo is born, actually there's one lump of nervous material which splits into brain and stomach. And briefly about neurons, okay? So here you see like an illustration of what a neuron can look like. It has sort of, think about it as many input devices. There's some computational unit in the middle, and there's lots of output devices. Most of us here are engineers, I guess you can understand that. The interesting thing about neurons is they have some electric behavior. They display a behavior we call action potential. Basically, when you stimulate it in a certain way, it will respond in a certain way, and this is the response you get. So sometimes when you look at, for example, an EEG or something, you see these sort of spikes. The interesting thing, anybody here electronic engineers? So those of you who are engineers, you may recognize this equation which describes the way neurons actually work, and it's very similar to how semiconductors work. And that's again, that's again not a coincidence, I think, because that's how nature works. The basic premise is this soup, which our brain is sort of still swimming in with different ions, has different concentrations of different ions, and inside the cell there's a different concentration, and the difference of the concentration of those ions leads to very interesting behavior, I should say. Okay? Electrical behavior in this case. You can think of the neuron to be performing a sum operation of its inputs, and if the sum is large enough, it produces an output. At the output of the input of the neuron sits the input of the next neuron. And this connection we call the synapse, as you can see here. And it's basically the gap, if you want, between two neurons. Now, while the neuron is electrical, the synapse is a chemical device, or a chemical mechanism. I don't want to get into the biophysics too much again. But basically, things we call neurotransmitters are being released at one end, and then they sort of propagate through to the other side, and they elicit the next response. And the interesting thing is, while the neuron is sort of doing the computation, the summing, the synapse is doing something which we attribute to memory and learning, because it has variable strength, which is, again, like I don't want to get into that. What? Okay. So the brain is pretty amazing. It's a very, very simple concept. Okay, a network of those little cells, the rules of the brain are very simple, and this amazing thing gives rise to so many things like emotions, thoughts, sensation, and realities, if you think about it. Okay. And I've got a quick comparison between brains and computers, which I will not go into, but the brain is pretty amazing as compared to computers, okay? We can look at that later. I'm going to skip the slide. This is what neuromorphic hardware looks like. An example, very, very simple circuit, integrated on a chip. 8,000 neurons we have on this chip. And with this hardware, with this electronics, we do very interesting stuff. Now, let's have a brief look at science today. I'm going to skip this because this is neuroscience again, but basically this tells us that we are not actually making our own decisions. The brain is making a decision before we realize we have made that decision. Okay? Some look at neuromorphic hardware. I'm going to finish off, okay, some look at neuromorphic hardware today. A silicon retina, which works exactly the same way our eye works, which is different to the way most cameras work. They give very interesting sort of pictures. They're different to the normal pictures they use from cameras. There's some hardware that I've built myself. You skip through that. And I want to leave you with some interesting questions, okay? Given that we've sort of understand what I've now taught you about the brain, which is, it's a very simple sort of collection, a very simple collection, but very complex collection, I should say, of cells, which gives rise to this intelligent behavior. Now, we agree that a rock is probably not very intelligent, but what about a fly? A fly is a brain. What about a clockwork? I wouldn't say it's very intelligent, but you can see again the similarities between a small mechanism which gives rise to something more intelligent. And we've got Einstein. I'm going to skip this one. Similarly, what is free will? The experiment I couldn't really talk about earlier indicates that our brain makes a decision before we have the illusion of having made the decision. Which leaves us the question, do we actually have free will? Similarly, if we have free will, then why couldn't a machine which has the same hardware as we do have free will as well, or emotions? Okay? And the final thought I want to leave you with is, can you think of anything that's similar to the brain that the man has, a man-made machine that we have built? Anybody? Okay, so we've built supercomputers, but they work in a drastically different way. No, actually, the internet is becoming more and more like the brain. Now, we didn't look at at the table of comparison that I showed you earlier. But if you look at the structure and the architecture of the brain or the internet, where if you want a computer is a node, then we see a lot of similarities. Okay, I'm being cut off here. Find me later if you want to know more. I think it's a fascinating topic, and I hope you agree.